Okay, so we're looking at inductance for a solenoid. In a circuit diagram, a solenoid usually looks something like this. So it's not jaggedy, it's kind of a couple loops. And we'll define inductance as L equals to the magnetic flux divided by the current. What I want to show you is that an inductor behaves a lot like a capacitor. Okay? An inductor stores energy in the magnetic field that it has created. So compare that to capacitance, which was Q over delta V. Okay? So a capacitor stores charge based on how much potential difference we set across the capacitor. An inductor has a certain amount of flux based on how much current is going through it. Okay? So imagine the inductor is like storing flux. Does that make sense? If a capacitor stores charge, an inductor stores flux. What creates the charge on a capacitor is the potential difference. What creates the flux in an inductor is the current. Okay, when charges flow through an inductor, that's how you create that magnetic field or that magnetic flux. Okay, so if you go through the math, we eventually see that for a solenoid, it is mu naught n squared A over L. Okay. So mu naught, that's just the permeability constant. N is the number of loops. A is the area of the solenoid, and L is how long that solenoid is. So you can write it like this, or you can write it like this: mu naught little n times NA. That little n is like your coil density, or the linear, density of how many coils per length. But regardless, if you look, this is all geometric. It's all based on the coil or the shape of the solenoid. The same way that we had shown that the capacitance is only dependent on the shape of the capacitor too. It was something like A over epsilon naught D, I think. Let me double check that. Oh, where's the equation? Sorry, epsilon naught is on the top. That was this one, right? The capacitance is only dependent on the shape of the capacitor. The inductance of an inductor. So this is an inductor, and you measure its inductance, and it's only dependent on its shape. How many loops? How long is it? How big is it? That's it. We measure inductance in henries. 1 Henry, which is 1 capital H, equals to 1 Tesla square meter per amp. Okay. Yeah.
So how do you go from n squared, or big N squared, to little n times?
So yeah, little n is big N over L. It's like how many loops per length. How compact. That little n measures how compact your coils are. Right, so this is n squared.
Right.
So So it's like a N over L in here. And then times NA. I think
Where did the L go initially?
the L was on the denominator.
Right, because when you take the magnetic flux, then you'll get mu naught NA by L, right? And then
So, yeah, we can go through those steps. And this is on page 985.
oh, I see. Okay.
Okay. Okay, so if this thing we measure, inductance, is the magnetic flux divided by the current going through it, and we set that as it is changing, as the magnetic flux changes, we create some sort of potential difference, then we can actually look at how the potential difference in an inductor, the EMF that is created, is equal to this. Okay? So, in other words, here we can actually back up just a little bit. The EMF created is, according to Faraday's law, the rate of change of this flux, right? The rate of change of this flux. But when you substitute in your inductance, we said that the inductance is just purely based on shape. It's constant. Okay, it's constant. So essentially what is changing your flux is the current. It's the current. So that works out to be this. Okay, so the induced EMF is directly proportional to the rate of change of current. That is really important. That is, you know how there's Ohm's law, like the rate of the the voltage drop from a resistor is V equals IR or something like that. This is essentially the relationship for a inductor. How does it fit into a circuit? How does it influence your current? And how does it influence the potential, electric potential? It's equal to this. You can also write it like this. Delta V of an inductor is equal to negative L di dt. And so the convention works as shown here. You gotta be very careful about how you consider whether the potential is going down or the potential is going up. So the potential decreases if the current is increasing, and the potential increases if the current is decreasing. So if there's current going through here and it's constant, there's no potential drop. It's only if it's changing. Okay, if it's increasing downward, it's going to create a backwards EMF up to resist the change. So it will be a potential drop, right, because it's resisting. If you're decreasing current, it's going to try and pump more charge through to resist the change again. And so it'll be like a potential jump. It's trying to push it. Okay, so what is considered plus or minus? Well, it really depends. It depends on if you're decreasing current or you're increasing current. So that's where the minus comes in. You gotta be careful about that. For a resistor, it's pretty straightforward. It will always drop across a resistor. Wherever the current's going, potential will drop across that resistor. Yeah.
So is inductance just a property of the material?
Inductance is a property of the geometry, not even the material. although kind of like with a capacitor, you can put the dielectric in there. With an inductor, you can put a core. You can put like iron, like an iron core into the inductor, so you can manipulate how sensitive it is to magnetic flux. I don't know if it really talks about that here. I don't think it does, but that's something you can do. Okay. Any questions about what an inductor does or inductance in a circuit? We'll kind of visit a little more with it. But for now, here's an interesting analysis or scenario to look at. Let's say you have this battery and it's attached to a switch, okay, and you have constant current flowing through. If you open the switch, you are trying to instantly turn off the current, right? You'll instantly turn off the current. So if you look at the potential across your inductor, it's based on the rate of change of the current. This is one of those inductors are kind of interesting because they're not limited by what the battery was doing. You can get more potential here than what the battery was putting out initially, because it's only just based on the rate of change of the current. If you try and turn off the current instantly, it will try and resist it. It'll try and create a bunch of current in the other direction to resist it at such a high potential that sometimes you'll get a spark. Because the potential is so great, much greater than what the battery was, and it'll force charges in the other direction because you tried to turn it off instantly. And so, well, you can get a spark, which is actually, yeah, one way you can, well, have like a spark plug or something like that. It's just like coil of wires, which is quite interesting. You can do something like that. Okay? Yeah?
I just wanted to confirm that the inductor acts as an EMF.
It does.
Okay.
It can push. It can push or resist charges.
And while EMFs get store their electromagnetic potential with chemical materials, inductors go through magnetic fields.
An EMF is a general term for anything that can push charges. So you can have a battery as an EMF. You can have a generator as an EMF. You can have an inductor as an EMF. As long as it is pushing charges, right? Whatever you would consider an electromotive force, something that can push charges. Or you can say it's a source of energy. Okay. So again, it's important to understand when we're looking at an inductor, really try and it is analogous to a capacitor. Where a capacitor stores charge, a inductor stores magnetic flux. As you try and change the magnetic flux, that's where you're storing or releasing energy. Yeah.
How do you add inductors? Like with capacitors, you
So, because it's based on the changing current, I imagine that if they're in series, the changing current is the same for both. So, well, it's not something I've thought about because it's not a question that ever comes up, to be honest. But I bet you could do an analysis on that, just doing Kirchhoff's loop rules, right? If you look at, you would have to add potentials if they're in series, but they would have the same current. So I imagine they behave a lot like resistors. Except that instead of with current, it's with rate of change of current. I think it should still just be adding it up. I think they should behave a lot like resistors. Because if you compare this to how a resistor works, oops, right? It's just, instead of I, it's di dt, right? So I think it should be a lot like a resistor. Okay, so how about the energy stored in an inductor? How do we actually measure that? if you look, it's very much similar to a capacitor. So for an inductor, you have the potential is 1/2 Li squared. This I could be, this is specifically if you take an inductor and you cut all the current out. Notice that they're integrating from 0 to I. So we can find the total energy stored in an inductor by integrating this equation from I equals 0 to some final current I. So sorry, they're charging it up, right? As you go from 0 current to some constant current, how much energy ends up being stored in there? It is that much.
Is that an IDI or an LDI?
This is IDI. Yeah, it must be IDI. Okay, so compare that to the potential in a capacitor is 1/2 CV squared. So again, for an inductor, it's the current that is causing the storage of energy, whereas a capacitor is the voltage that's causing the storage of energy. And where is that energy stored? In an inductor, it's stored in the magnetic field. In a capacitor, it's stored in the charge separation. Okay? Stored in the field. Okay. Any more questions on inductors? Some really good questions so far. All right. Okay, let's look at some application of inductors. First, we'll do LC circuits. Now this time, I've kind of been skipping through the math a little bit, but it's going to be important that you guys can actually do this math for some of these. So let's look at an LC circuit, and it looks something like this. Okay, so I'm going to actually draw this diagram so we can work with it. Okay, so you have some capacitor. When we say LC, it's an inductor capacitor circuit. Starts positively charged on one side, negatively charged on the other. There's some capacitance for this, and it's initially charged at Q0. So there is some potential difference here. Okay, so if we do Kirchhoff's loop rule, once we close this and the charges get to flow, the charges will flow fastest in the beginning as it's trying to discharge. So it's kind of interesting because, well, we'll see in just a second. Let's go ahead and just do Kirchhoff's loop rule on this. The potential across the capacitor and the potential across the inductor should add up to 0. Okay, so the potential across this is Q over C. Whereas the potential across this is minus L di dt equals to 0. Okay, or we can say that Q over C equals to L di dt. Or we can say Q. Actually, I'm going to write it like this. 1 over 1 over LC times Q is equal to di dt. Okay. So how does the current relate to the charge? You get current as you lose charge. So the current is equal to the negative rate of change of Q with respect to t. Which means then that when you put these two together, You get 1 over LC Q equals to negative d squared Q dt squared. You get the second time rate of change of charge is related to this on the left-hand side. This is going to come up a couple times, but this is a differential equation because you have a variable Q related to its rate of change. We've talked about this a little bit before. You need to recognize this kind of differential equation, though. This is very specific. I'm going to write it like this. D squared Q dt squared is equal to negative 1 over LC times Q. In other words, the second order time rate of change of the variables is equal to the negative of that variable. The negative is kind of important. It is kind of demonstrating that it's resisting. It's like the rate of change is negative to whatever its state is. If that makes any sense. No. Okay, that's fine. You know what? When we get to springs, it'll make a lot more sense. Basically, this is like a restorative force. This is like a restorative behavior. The rate at which your charge changes is negative to whatever the charge is. In other words, the more charge you have, the more it's trying to decelerate. Does that make sense? Think of this as like an acceleration. The acceleration is equal to the negative of whatever its value is. Let's compare this. It's going to be really important. Let's compare this to a spring. A spring that is stretched out and then released. So let's say there's some equilibrium position, x naught, and there's some change x. Right? If you do Newton's law on this, you would get that the sum of the forces is equal to negative kx equals to m d squared x dt squared. It's like F equals ma, right? Here's the force, going back a little ways, going back to spring Hooke's law, right? But the force is resisting the stretch, right? It's backwards. And so you can write negative k over m x equals to d squared x dt squared, right? It is a restorative force. The acceleration is towards the center, and it's greater the further away you are. It's the same thing here. The rate at which you lose charge is greater the more charge you have. It's like it's trying to bring it towards some sort of center. So we've tried this before. What kind of function, if Q is a function of time, what kind of function is related to its second order derivative? Exponential, or there's another one that is the same as it's similar to its second order derivative. Yeah. Trigonometric functions, sine or cosine, right? Sine or cosine. So when we solve for this, we can guess a function. And you know what? At this point, let's go ahead and try and solve these in parallel, like side by side, because you'll see that they are very, very similar. So we can say that what if there's some function x that has some amplitude, we'll say like x max, times cosine of some omega t plus phi. So this is the most general form of a trigonometric function, right? And in the same way, then we can say q is equal to some q max, cosine of omega t plus phi, right? Okay, so all we gotta do is, let's do a couple derivatives here. So x prime, or, well, all right, here, let's not use prime. dx dt, so just chain rule. This would be omega x max negative sine omega t plus phi. Second order derivative would be negative omega squared x max cosine omega t, omega t.
Is X max a constant?
X max would be a constant, whatever you start at, right? It's like an amplitude. The most general form of a trigonometric function is like amplitude times cosine or sine, and then the stuff on the other side. Vika again. Okay, omega t plus phi. And so we can do the same thing on this side, dq dt. Just write all this stuff out. Negative omega q max cosine omega t plus, or sorry, shoot, this should be sine. And then you have the second order derivative. Negative omega squared, you got all that stuff, cosine. Okay, so let's plug them in. Okay, we're going to plug them in back to that original equation up here. So if I plug these two in, on the left-hand side, I have negative km, negative k over m, times x, this is x, on the right-hand side, I have this, which is just d squared x dt squared. So negative omega squared x max cosine of omega t plus phi. If you look, they both have an x max cosine omega t plus phi. So actually, all of that cancels out, and you get k over m equals to omega squared. In other words, in order for this behavior to work out, in order for the second order derivative to equal to this x, or negative k over m times x, omega has to equal the square root of k over m. This is what we call the natural frequency of this oscillator, this spring block system. In the same way, if you look at this and you plug it back in, what you'll see is then omega equals to the square root of 1 over LC. Okay? So in general, any kind of physical property that has this kind of equation set up, some, I'll just use capital A, some variable x equals to, or negative ax dx, d squared x over dt squared. This is, in general, what we call simple harmonic motion. Okay. Anything that has this kind of structural setup will have a solution. X is some trigonometric function. And the frequency, which we'll call the natural frequency, will always be the square root of A. They'll always work out that way. They'll all behave this way. And we'll kind of explore some more of these next time. But
How do I use it? What am I supposed to do?
I mean, it would be an imaginary use.